Welcome. I am so thrilled to have you here with us today for this custom tailored deep dive.
Yeah, it's great to be here.
We have an incredible mission for today's session, and it is something that I promise is going to completely change the way you look at complex problems. We are exploring a concept that acts like, well, a literal cheat code for the
A
universe.
literal cheat code, yeah.
Imagine you're staring at a problem that is just impossibly tangled, completely chaotic, and you are just hitting a brick wall over and over. What if you didn't actually have to work any harder to solve it?
Right.
What if you just needed to look at it in a completely different kind of mirror?
And that is really the core premise we're investigating today. To pull this off, we are diving into a really fascinating stack of sources you provided us. We have a translated article titled The Elegance of Geometric Inversion, a visually striking slide deck called the Inversion Mirror, and a wonderfully comprehensive, albeit dense, mathematical paper by Tom Davis.
Yeah, that paper was intense.
It was. But by the end of this deep dive, you are going to understand how a concept called geometric inversion allows you to take complex, curved reality and magically flatten it into simple straight lines.
Okay, so let's unpack this. What is the basic engine that actually drives this mathematical magic trick? The sources describe it as a mathematical mirror, but obviously we aren't talking about reflecting across a flat piece of glass like the mirror in your bathroom.
No, not at all.
This is a reflection across a circular boundary. So let's imagine you draw a circle on the ground. We will call it circle K. It has a center point O and a certain radius R. From what I gather, in this inverted world, everything inside that circle gets thrown to the outside.
Right.
And everything outside gets pulled to the inside. But how does that actually work in practice?
It revolves around a very strict, beautiful, inverse proportionality. Think about standing inside that circle you just drew. If you take a point, let's call it your original point P, and you want to find its inverted twin, P prime, you just measure the distance from the center O to your original point. Then, you multiply that distance by the distance from the center to the new inverted point. That multiplication will always, without fail, equal the radius of your circle squared.
So just to make sure I'm visualizing this correctly, let's say our circle has a radius of 10 feet. 10 squared is 100.
Exactly.
If I place my point P just 2 feet away from the center, its inverted twin has to be 50 feet away because 2 times 50 gives us that 100.
You are visualizing it perfectly. And if you walk your point P right up to the boundary of the circle, so 10 feet away from the center, your inverted twin is also 10 feet away. 10 times 10 is 100.
Oh, I see.
So any point sitting exactly on the circular boundary just stays right where it is.
Yeah.
It's the one place where reality and the inverted world perfectly overlap.
That makes sense. But wait, if I push my point P even closer to the center, say it's only 1 foot away, the inverse twin has to shoot out to 100 feet away to maintain that balance. Doesn't that create a massive problem? Like, what happens if I try to invert the exact center point, point O? As I get closer and closer to that exact center, my inverse twin is shooting further and further away at incredible speeds. If I hit the dead center, where does the twin go? Doesn't that just break the math?
Well, if we connect this to the bigger picture, this is where mathematicians had to get incredibly creative. Standard flat geometry, what we call the Euclidean plane, it couldn't handle that paradox.
It just breaks down.
Exactly. So to solve the problem of the center point, mathematicians literally extended the plane to include a single theoretical point at infinity.
A point at infinity? How do you even picture that?
Think of it like a classic vintage arcade game, like Pac-Man. You know how if your character walks completely off the right edge of the screen, they instantly loop back and appear on the far left edge?
Oh, absolutely. The screen wraps around itself.
In this extended mathematical universe, the entire flat plane loops back on itself through infinity. No matter which direction you travel up, down, left, right, if you go infinitely far, you end up at the exact same point at infinity.
Wow.
So when your point P sits exactly on the center of the inversion circle, its twin is resting comfortably at that point at infinity. And in this new wrapped around reality, straight lines are no longer just straight lines.
What are they?
They're actually just circles that happen to possess an infinitely large radius and pass right through that point at infinity.
That is wild to wrap my head around. A straight line is just a massive circle that loops through infinity. So if straight lines and circles are fundamentally the same thing in this universe, how do we use that to solve problems? There has to be some kind of translation dictionary between our world and the inverted world.
There is, and it boils down to one absolute golden rule. The most important rule for problem solving here is this. Any circle that passes through the center of our inversion mirror becomes a straight line that does not pass through the center.
Wait, really? A circle just instantly snaps into a straight line.
It does, and the why behind this magic trick is what makes it so powerful. It is a process of dimensionality reduction. By deliberately placing your inversion center, that point O, right on top of a problematic complex curve in whatever geometric puzzle you're trying to solve, you literally flatten that difficult circle out into a simple straight line.
I see. You are taking complex pure geometry with all of its agonizing curves and messy intersections and flattening it into something you can measure with a simple ruler.
You're swapping a difficult geometry problem for a simple algebra problem. Now, it is true that the overall shapes themselves get totally warped in this process. One of your sources notes that if you inverted an elephant, it would turn into a highly distorted, unrecognizable puddle of geometry in the inverted world.
A very mathematically precise, very confused puddle.
Exactly. But, and this is the crucial part for problem solving, the angles of intersection between lines are perfectly preserved. If two shapes are barely kissing, just perfectly tangent to each other in reality, they remain perfectly tangent in the inverted world.
So the relationships survive.
Yes, the shapes warp, but their relationships to one another remain absolutely rock solid.
Let's look at a concrete example of this dimensionality reduction from the sources, because I think this is where the genius really shines. The slides outline this classic math headache called Ptolemy's theorem.
Oh yes, Ptolemy.
For anyone who hasn't had to prove this recently, let me set the scene for you. Imagine a cyclic quadrilateral. That is just a four-sided shape, like a wonky kite or a rectangle, where all four corners touch the edge of a surrounding circle. Let's call the corners A, B, C, and D.
Right.
Ptolemy's theorem states that the product of the diagonals equals the sum of the products of the opposite sides.
It's a mouthful just to say it.
Exactly. Trying to prove that mathematically with standard geometry is a nightmare. You have to draw a bunch of auxiliary lines, find similar overlapping triangles, track complex internal angles. It is tedious. But the sources say inversion fixes this instantly. How does our geometric cheat code actually solve Ptolemy's theorem?
It's brilliantly simple. You take your center of inversion, our magic point O, and you place it precisely on vertex A of that four-sided shape.
Okay, so the center of our mirror is now sitting right on one of the corners. But since that corner is touching the surrounding circle, that means the surrounding circle passes right through the center of our inversion.
And what is our golden rule?
Any circle passing through the center of inversion becomes a straight line. So that entire surrounding circle gets completely flattened.
It flattens entirely. And think about the other three corners of your shape, B, C, and D. They're all sitting on that circle. So when the circle unrolls into a straight line, those 3 points are inverted into 3 new points, B prime, C prime, and D prime. And they are now sitting perfectly in a row on a single, straight, flat line.
Oh, wow. That is a massive aha moment. You take this complex, headache-inducing theorem with intersecting diagonals and surrounding circles, and you reduce it instantly to the most elementary logic we teach to kids in grade school.
Exactly.
If you have 3 points on a line, B, C, and D, the total length of the line from B to D is just the first piece plus the second piece, B to C plus C to D.
It really is that simple. Through the strict distance formulas of inversion, that basic line addition perfectly translates backwards into Ptolemy's complicated multiplication theorem. You didn't do harder math, you just changed the geometry of the problem to avoid the hard math entirely.
Here's where it gets really interesting, because this isn't just about abstract circles on a chalkboard. I loved reading the Tom Davis paper because it shows how this theoretical mathematical cheat code actually solved a centuries-old physical engineering bottleneck. We are talking about the Industrial Revolution.
A huge turning point.
For hundreds of years, engineers were stuck on a seemingly impossible mechanical problem. How to mechanically convert the perfect circular motion of a steam engine wheel into perfect linear motion.
It was a massive hurdle. If you want a piston to drive straight or a pump to move perfectly up and down based on a spinning wheel, you typically have to use tracks or guides. But guides create friction, and friction wears down metal over time. They needed a linkage system of hinged bars that inherently, mathematically produced a straight line from a circle, with no tracks required.
And no one could figure it out, until they applied inversion. The paper details this device called Poiseuille's linkage. It is essentially a physical mechanical manifestation of our mathematical mirror.
It is a gorgeous piece of engineering. It uses a series of hinged metal bars to physically force a constant inversion relationship. Picture a diamond shape, a rhombus, made of 4 equal length metal bars, completely flexible at the joints. Let's call the length of those rhombus bars L.
Okay, I'm picturing it.
Now, attach 2 opposite corners of that rhombus to a fixed anchor point using 2 longer metal bars, which we'll say have a length of R.
So you have this flexible diamond anchored back to a single pivot point.
Right. And because of the rigid geometry of those physical metal bars, the 2 free corners of the diamond, let's call them point A and point A prime, are trapped. The math dictates that the distance from the anchor to point A multiplied by the distance to A prime will always equal a constant value based on the lengths of those metal bars. Specifically, it equals L squared minus R squared.
But wait, a distance times another distance equaling a constant, that is the exact definition of geometric inversion.
It is. Points A and A prime are physically mechanically locked in as inverse twins. So what happens if you add one more small metal bar to force point A to move in a circle that passes right through the anchor point?
Our golden rule strikes again. A circle passing through the center of inversion becomes a straight line. So as point A spins in a physical circle, the metal hinges physically force point A prime to flawlessly draw a perfect, infinite straight line in the real world.
Flawlessly.
That is incredibly satisfying. An abstract philosophy about a point at infinity literally gave engineers the mechanical gears to drive industrial pumps and engines without friction guides.
It highlights perfectly how abstract mathematics often predates its physical applications. Sometimes you just have to discover the underlying logic before you can build a machine. And this logic is incredibly useful for solving other seemingly impossible spatial puzzles, especially involving trap shapes.
Yes. Let's talk about the four-circle problem from the slide deck. This is such a fun visualization. Let me try to set the scene for you listening. Imagine a flat, straight ground line. Resting on that line are 2 large circles, say the size of bowling balls. They are touching the ground and they are touching each other. Now, tucked into the little gap right between those 2 big circles, also resting on the ground, is a third, smaller circle. Think of it like a baseball.
So we have 3 circles all resting on the floor, all touching.
Right. Finally, resting right on top of that baseball, wedged right in the middle valley between the 2 big bowling balls, is a tiny 4th circle. Let's call it a marble. We are told this tiny trapped marble has a radius of exactly 1 centimeter. The puzzle asks, what is the exact height of the center of that tiny trapped marble from the ground line?
If you try to solve this with standard algebraic geometry, finding the coordinates of all those tangent kissing points, it is agonizing. You are setting up pages of simultaneous quadratic equations, trying to figure out where all those curves intersect. But inversion offers an elegant escape route.
We don't want to fight the curves, so we invert them. But how do we choose where to put our center of inversion for this puzzle?
We want to flatten the boundaries that are making the problem difficult.
Yeah.
So we place our center of inversion exactly at the point where the 2 big bowling ball circles touch the ground line. By doing that, both the ground line and the 2 big circles pass right through our inversion center.
Which means they all turn into straight lines. The ground becomes a straight line, and the 2 big circles warp into straight, parallel, vertical walls. Our tiny trapped marble is no longer sitting in a complex, curved valley. It is simply trapped in a perfectly straight, linear elevator shaft between 2 parallel walls.
The complex geometry just collapses. When you work out the simple arithmetic of that flattened elevator shaft, you find that the parallel walls are exactly 4 units apart, which means the geometry of the bigger circles in our simplified world has a radius of 4.
And since our tiny marble is just stacked perfectly in this straight corridor, calculating its height is a breeze. It's basically simple addition. The solution falls right out. The height is exactly 7 centimeters. We bypassed all the quadratic nightmares.
It is a masterclass in avoiding unnecessary complexity. And this same principle of flattening boundaries applies to an even more elaborate puzzle known as the Steiner-Porism.
I love the Steiner-Porism. Imagine you have 2 boundary circles, one sitting entirely inside the other, but they are off-center, totally asymmetrical. Now imagine drawing a chain of smaller circles in the gap between them, with each new circle touching the inner boundary, the outer boundary, and the previous circle in the chain. Think of it like a beaded necklace trapped between 2 rings.
A great way to visualize it.
The big question is, if you keep drawing circles around that awkward gap, will the chain ever connect perfectly back to the starting circle without overlapping or leaving an ugly gap?
If the two boundary circles were perfectly concentric, meaning they shared the exact same center point like a bullseye, the answer would be obvious. The gap would be uniform everywhere. So if a chain of identical beads closed perfectly once, you could just rotate the whole necklace like a ball bearing, and it would always close perfectly no matter where you started drawing the first circle. But our boundary rings are off-center and awkward. The gap gets wider on one side and narrower on the other.
So how do we fix it? We use inversion to manufacture perfect symmetry, but where do we place the mirror to force two off-center circles to become a perfect bullseye?
This raises an important question. The Tom Davis paper explains that every pair of non-intersecting circles has something called a radical axis. It sounds intimidating, but it's just a specific, invisible straight line running between them. If you stand anywhere on that radical axis and you draw tangent lines outward at both circles, those lines will be exactly equal in length.
So you find that magical radical axis and you deliberately place your center of inversion right on it. When you run the mathematical mirror, those two awkward off-center circles instantly warp and invert into a pair of perfectly concentric bullseye rings.
And remember our rule about preservation. The fundamental laws of tangency, things touching each other, are perfectly preserved during inversion. So whatever happens in our perfectly symmetrical concentric world must also be true in the awkward off-center reality. If a chain of circles closes perfectly with one starting position in the bullseye, it will close perfectly with all of them in the asymmetrical world. You've proven a complex truth about a RESI system simply by forcing it into symmetry.
It's like finding a hidden, pristine order underneath all the chaos, which perfectly transitions us to the final, truly mind-bending concept from our stack of sources, Descartes' theorem and infinite fractal beauty.
René Descartes, the famous philosopher and mathematician, formulated a way to calculate the relationship between any four mutually tangent circles, meaning four circles that are all perfectly kissing each other at the exact same time. To do this, he defined the curvature of a circle. We'll call curvature K. He defined it simply as 1 divided by the circle's radius. So a circle with a radius of 2 has a curvature of 1 over 2. A small circle with a radius of 1 over 4 has a curvature of 4.
And what's brilliant is how this definition treats a straight line. We established earlier that a straight line is just a massive circle with an infinite radius. So 1 divided by infinity means a straight line has a curvature of exactly 0.
Descartes' theorem proves that the curvatures of any four mutually kissing circles are locked in an elegant relationship. Basically, if you square the curvatures of all four circles, add them together, and multiply by 2, that number will always equal what you get if you just add the four curvatures together first and then square the total.
The formula itself is incredibly neat, but the sources reveal a remarkable secret hiding inside it. If you have four mutually touching circles and all four of them happen to have a curvature that is a perfect whole integer, like 2 or 3 or 15, then the entire infinite chain of circles they can generate will also possess perfect integer curvatures.
It's amazing.
You can keep drawing smaller and smaller kissing circles in the tiny gaps between them forever, and every single one of their curvatures will be a clean whole number. It never devolves into messy decimals.
But what's fascinating here is what happens when we combine this integer rule with geometric inversion. Specifically, what happens if we anchor our circles to a straight line? Remember, a straight line has a curvature of exactly 0, which is a perfect integer.
This was the ultimate aha moment for me reading the sources. By resting these tangent circles on a straight line, we generate an infinitely repeating, infinitely shrinking pattern of circles nestled between each other. The sources call them fairy circles, or Ford circles.
And the beauty of these fairy circles is that they perfectly map the rational number line. Imagine a ruler representing the space between 0 and 1. If you drop this infinite chain of circles onto that ruler, every single possible fraction you can think of, 1/2, 1/3, 5/8, 13/21, has a specific circle resting exactly on that point on the ruler.
And its radius is precisely defined by the fraction it sits on. It is a perfect infinite fractal map of fractions, all generated by understanding how curvature, straight lines, and inversion interact. It is like discovering the secret source code that renders the mathematics of the universe.
It truly is. It shows that beneath seemingly chaotic tangles of curves, nested gaps, and infinite fractions, there is a profound symmetrical elegance waiting to be uncovered, provided you know exactly how to look for it.
So what does this all mean? We've talked about ancient math theorems, Industrial Revolution mechanics, and infinite fractals. But to bring it back down to earth for you, the listener, geometric inversion is much more than just a mathematical formula to help you pass a geometry test. It is a fundamental philosophy of perspective.
The core takeaway from all of these sources is that when a problem seems hopelessly unsolvable, when it is tangled in curvature and complexity, you feel like you're hitting a wall, you don't necessarily need to work harder. You don't always need to learn more complex math or apply brute force. You simply need to step back and find the right mirror. You need to change your geometry. By moving your point of observation, the impossible flattens out into simple addition.
I love that. And that leaves us with a final thought I really want you to mull over today as you go about your week. We have seen how geometric inversion flattens math and mechanics, but think about how this philosophy could apply to modern systems. Imagine computer algorithms sorting massive, chaotic data sets, or city planners trying to route traffic through a tangled, historic grid. What if those modern bottlenecks could be instantly resolved not by adding more computing power or building wider roads, but by identifying a systemic center of inversion? A radical shift in perspective that flattens the chaotic data into straight, parallel lines. Think about what the center of inversion might be in your own field and see what happens when you look through the mirror. Thank you so much for joining us on this deep dive.